We spent so much time developing the directional derivative, it's time to find some. So we have a paraboloid, which we all know what that looks like. It looks kind of like a bowl. So it's going to be facing up like this, right? So that's z is equal to f of xy, which is x squared plus y squared. So there's our paraboloid. And we want to find the indicated directional derivatives. Now, before I go into any of this, I'm going to find the gradient of f just because it'll be easier for me down below. So the derivative of f with respect to x would be 2x, and the derivative of f with respect to y would be 2y. So we'll keep that in mind as we move down. Okay, so our first spot will be at 0.11. So keep in mind, this is an x value, and that's a y value that we're going to substitute into our gradient. Yes. Now here's our direction. It's tempting to say, oh, that's u, but it's not. So you have to remember that, and it was kind of tucked in there, but it has to be a unit vector. So your unit vector u, and 1, 1 is not a unit vector, right? It's not a vector of length 1, so we're going to have to turn it into a unit vector real briefly. So that would be 1, 1 divided by the square root of 1 squared plus 1 squared. 1 squared plus 1 squared is 2. So this is really 1 over the square root of 2, 1 over the square root of 2. Okay, so now we're ready to go. So the directional derivative of the function f in the direction of u would be equal to the dot product of the gradient and the unit vector. Okay, so that would be 2, but instead of x, I'm going to put in my x value of 1, and then 2 times 1 for my y. There's my gradient. Dot product with 1 over the square root of 2, 1 over the square root of 2. Or if you like, you can rationalize them in your head. It's square root of 2 over 2. It's not that important. Okay, so if I multiply, this is 2. 2 times that would make 2 over the square root of 2 plus another 2 over the square root of 2, which is 4 over the square root of 2, which is about 2.83. There we go. And yes, you could rationalize that. It's what? 2 square root of 2 if you wanted to know. Right, if you want it rationalized. Okay, so what about if we start at that same point, but instead of going this direction, we go the opposite direction? Well, the unit vector on that one's pretty easy because it's the same as what we already did. It'll be negative 1 over the square root of 2, negative 1 over the square root of 2. Right, and this is still our x and our y right here. Okay, well that's easy enough. So then we're going to take the dot product of 2 times 1 and 2 times 1. And we're going to dot product it with the negative 1 over the square root of 2, negative 1 over the square root of 2. And we already knew where this was going. Indeed, it's the same as the other one, except it's negative. Unsurprisingly. All right, now what about if we start at the origin and we head in the negative 2, 3 direction? So here's our x, here's our y, and we want to make that a unit vector. But let's just think about this for a second. We don't need to bother making a unit vector out of this because think about what's going to happen to our gradient here. When we get to over here, this would be 2 times 0, which is 0, and 2 times 0, which is 0. Sorry, my 0 looks like a theta there, and I did not intend that. It's supposed to be 0. Which is going to be 0, 0, right? So whatever u is, when we dot product it with it, it's going to be 0. So this would just be 0 plus 0, which is 0. All right. Next, what if we go 2, 5? So there's our x and there's our y. I'm just going to write that for the last one also. And then we want to make a unit vector out of 3, 4. Okay, so that would be 3, 4 divided by the magnitude of that, which is 3 squared plus 4 squared. That's 16 plus 9, which is 25. And the square root of 25 is 5. So this is 3/5 and 4/5. Okay, so when I want the directional derivative, I'm going to take the dot product of, and of course it's not just 2, it's 2 times 2 and 2 times 5, because those are the x and y values that I'm using. So that's 4, right? So this is 4, 10, dot product with 3/5, 4/5, which is 12/5 plus 40/5, which is 52 over 5, or 10.4. Very steep, right? So at the origin, right, you're at the bottom of the bowl. There's no steepness, right? So that's what's happening there. No steepness, right? These are pretty steep. The ceiling above your head's pretty steep at 1, 1, go in one direction, go in the other direction. And then this one at 2, 5 and heading in that direction, it's getting real steep above your head. The ceiling above your head's getting higher and higher. Right, what if you start at that same point and go this way and go -5, 2? Then what could happen? Well, first I have to make a unit vector out of it. So -5, 2 divided by the square root of 5 squared plus 2 squared would be, let's see, that's 25 plus 4, so that's 29. So that doesn't make anything nice. It's -5 over the square root of 29, 2 over the square root of 29. Okay, so then for my directional derivative, that would be 2 times 2 and 5 times 2. I'm going to dot product with -5 over the square root of 29 and 2 over the square root of 29. And this is going to have an interesting result because 4 times -5 is -20 over the square root of 29. And then 25, oh, it's 2, not 5. I just knew I was doing y. There we go. Sorry, it's 2. It's 10. There we go. 10 times 2 is also 20, but it's positive. And it's 0. But it's 0 for a very different reason, right? It's 0 because we're going around the surface on a contour curve. It's not that the steepness is, well, if you think of the paraboloid, what's happening is you're starting at this point 2, 5, and instead of going up like we were in the one above or down like we were a couple ago, you're actually going around the contour curve, right? So the steepness isn't changing because you're going, the direction you're pointing is going around like a contour curve. And I did graph the paraboloid in Maple, just so you can see. I graphed it with Plot 3D, so it ends up with these sharp points here. That's just the way that works. And there is an operator called del, D-E-L, which is the gradient. So you can do it a couple ways. Gradient is also a command. And then you can show that you can take the dot product of the gradient. I shouldn't do it with 1, 1, though. That would be bad. I should do it with the one that was given, but well, the one that was given, but I should divide it by the square root of 2, because otherwise it's not a unit vector. So I'll do that. But again, this is strictly not necessary based on what we're doing. But we could do it this way and find a generic formula and then use that for all the answers. That's another way we could do this problem. But it only works for any particular direction. So this was built off of the direction 1, 1. If you're doing a different direction, then you'd have to go find it a different way. But it's comforting to know that Maple can check the answers for you or help you check the answers for yourself.